So I believe we did part A and B of this question. Is that correct? Can anybody tell me where we left off? And I think we were at part C.
Yeah, that's right.
Okay, thank you. So MRAM, we want to approximate the area under that graph from 0 to 4 using a midpoint rectangular approximation with 8 equal subintervals. So with 8 subintervals, then the width of each rectangle we can calculate by taking 4 and subtract 0. The reason I take 4 and 0 is because that's the interval on which I'm looking for the area. And I'm going to divide that distance from 0 to 4 by 8, and that will give me the width of each rectangle, or the width of each subinterval. Now you can see in the diagram there, I've drawn the first 3 rectangles. And so the midpoint of the first rectangle would fall at an x value of 0.25. And then from there, you're just adding 0.5 to get the center location of each rectangle. So the center of the second rectangle would be at x equals 0.75. And then when I add 0.5 to that, I would get 1.25, etc. So it's those x values. I have to plug those x values into the function to get the height of each rectangle, because the height is dictated by the midpoint of each rectangle. So rather than write 0.5, which is the width multiplied by the height 8 times, I've just written 0.5 outside the square bracket because the 0.5 is common to every rectangle. And I'm just going to multiply that by the height of each rectangle, which is f at 0.25 plus f at 0.75 plus f at 1.25 plus f at 1.75 plus f at 2.25, etc., all the way to f at 3.75. And then it's just letting your calculator do the work. So you have to plug all those values into the function. You have 8 values there you're going to add up and then multiply by the width of a half, and you should get 25.25. So that would be the midpoint rectangular approximation using 8 rectangles, or 8 equal width rectangles. Any questions on A, B, or C here for this example? Okay, so the next page, page 11, is just a summary of the different circumstances you can have for underestimation or overestimation for LRAM and RRAM. So in the top half of the chart, you can see that if a function is increasing, regardless of whether it's concave up or concave down, if the function is increasing, LRAM would give you an underestimate of the area, and RRAM would give you an overestimate of the area. And in the bottom half of the chart, you can see that if the function is decreasing, then it's the opposite of that. Regardless of whether the function is concave up or concave down, as long as the function is decreasing, LRAM would be an overestimate and RRAM would be an underestimate. You don't need to memorize that chart. It's best if you can just sketch the shape of the graph and draw one rectangle, and you can tell from just drawing one rectangle using LRAM or RRAM whether your area would be an underestimate or an overestimate. Okay, which brings us to page 12, which is the next or the last method that you can use to approximate areas under a curve. And it's using trapezoids. Now, trapezoids would improve the estimate as long as you're using the same, when you're comparing trapezoids with rectangles, whether you're using LRAM or RRAM, trapezoids would be better because you minimize the over and under estimate. And you can see that from the diagram. So if I have, in that first picture there, I'm using 3 trapezoids. You can see that those 3 trapezoids would be a better approximation than if I used 3 rectangles. Whether I used LRAM or RRAM, it wouldn't matter. The trapezoid would be a better approximation than both of those. So we need to know how to find the area of a trapezoid, and typically in all our problems, the trapezoid is going to look something like that yellow highlighted shape. Okay. I've given the sides labels. HL would be the height of the left-hand side of the trapezoid. HR, H subscript R, would be the height of the right-hand side of the trapezoid. Delta X would be the width. So you can write W if you want. That's the width of the trapezoid. And they're typically all going to have that kind of shape. The area is just the average of the 2 heights. So add up HL and HR and divide by 2. That would be the average. And then just multiply by the width. Okay. So you can see that the calculations, if we're going to be adding up a bunch of trapezoids, the calculations are more involved. Okay, so I guess more work gives us a better approximation. That's usually the case in life. More work equals a better result. So we're going to use that formula to sum trapezoids now rather than rectangles. Okay, so first example here, we're given the function x squared plus 1. Approximate the area between f of x and the x-axis from 0 to 2 using the trapezoidal approximation with 4 equal subintervals. So you're splitting the interval from 0 to 2 into 4 equal widths. So that's just 2 minus 0 divided by 4. So our width of the trapezoid is 0.5. And so our area approximation would be the area of trapezoid 1 plus the area of trapezoid 2 plus the area of trapezoid 3 plus the area of trapezoid 4. So we're accumulating area as we move from left to right. So you can see from the expression, since the width is 0.5, I've factored out the 0.5. And now for the first trapezoid, I'm going to average the 2 heights, which would be f at 0 plus f at 0.5, divide that by 2, and then multiply by that 0.5, which is outside the bracket. Then I move to the next trapezoid. The heights there would be f at 0.5 plus f at 1.0. Divide that by 2 to get the average. Then move to the third trapezoid. The heights, the averaging of the 2 heights would be f at 1.0 plus f at 1.5. Because you're finding the average, you divide by 2. And then for the fourth trapezoid, it would be f at 1.5 plus f at 2.0 divided by 2. And then I close the bracket. So I have 4 terms inside the square parentheses, and I'm going to multiply those by 0.5, which is the width of each trapezoid. Now I've highlighted the fact that f at 0.5 shows up twice, f at 1.0 shows up twice, f at 1.5 shows up twice in our expression for the area. But the first and last values, f at 0 and f at 2.0, do not show up twice. So we can write that expression in a condensed version. First of all, I can take the 1/2 that's common to each one of the 4 terms in the brackets. There's a 1/2 that's common. I can pull that outside the bracket and write 0.5 divided by 2. Okay. Then inside the square parentheses, you can see that I'm just left with f at 0 and then plus 2 times f at 0.5, f at 1, f at 1.5, plus just f at 2.0. So the first and last is just a single term, and then I've got 2 times each one of the partition points in the middle. So the 0.5, the 1.0, and the 1.5. And when you plug those values into the function and do the math on your calculator, you would get 4.75. Now I want to point out that kind of pattern will always happen when you're using trapezoids. So if you were using 6 subintervals, you would have still just f at 0 and f at 2.0, but then 2 times all the subintervals in between. That will always happen when you're using this trapezoidal approximation. Any questions on that? Okay, so now part B is saying approximate the area using LRAM and RRAM with the same number of subintervals we used for the trapezoidal approximation. So again, use 4 subintervals. So LRAM would just be, now you're subbing rectangles, so it's just the width, which is 0.5. For LRAM, the heights would be f at 0, f at 0.5, f at 1.0, and f at 1.5. Okay, when you plug those values in to the function and do the math, you get 3.75. For RRAM, the heights are f at 0.5, f at 1, f at 1.5, and f at 2.0. Multiply that by the width of 0.5, and you would get an area approximation of 5.75. And then the last part of the question asks, what's the relationship between the trapezoidal approximation and the LRAM and RRAM approximation? And you can see from what I've written there that the relationship is that the trapezoidal approximation will always be the average of the left rectangular approximation and the right rectangular approximation, as long as you're using the same number of intervals. So if you do a trapezoidal approximation with 10 subintervals, that will be the average of the LRAM and RRAM approximation using 10 subintervals. So as long as the number of subintervals or the number of rectangles and trapezoids is the same, that relationship will always be true. It's a useful thing to know on the AP exam because you may get a question where it says, yeah, use the LRAM and RRAM to find the area under a curve. So it'll ask you to do 2 different approximations. And then the third part of the question might ask you to do the trapezoidal approximation. Well, you can see from part A that there's a lot of calculations involved if you actually go and do the trapezoidal approximation. But if you already know LRAM and RRAM, all you have to do is find the average of the two and write down that the trapezoidal approximation would just be the average. So it's much less labor intensive to use that formula if you already know LRAM and RRAM. And again, the key point there to remember is it's only true for the same number of subintervals. Any questions on that? Okay, next example. Given the function 9 minus x squared, approximate the area between f of x and the x-axis from 0 to 3 using the trapezoidal approximation with 6 equal subintervals. Okay, there's nothing new here. This is just showing you that the calculations, the more trapezoids you use, the more calculations are involved. So again, you find the width. So in other words, you're just dividing the distance from 0 to 3 by 6 subintervals, and we get a width of 0.5. So you can see that I've written each area as a separate term. 0.5 times, for the first trapezoid, f at 0 plus f at 0.5 divided by 2. Then the next trapezoid, 0.5 times f at 0.5 plus f at 1.0 divided by 2. And you can see that there are six similar terms because there are 6 trapezoids. And again, I've highlighted the fact that each one of those partition points, like at 0.5, the 1.0, the interior ones show up twice, but the first and last ones show up only once. So you can go right to that last expression there that I wrote in black. It's just w divided by 2 multiplied by f at 0, and then 2 times the function evaluated at every partition in between, and then just f at the last point, which is 3.0. When you plug that into the calculator, you would get 17.875 as your area. So it's similar to the last example, only more trapezoids. But the pattern is the same. The next example is just the same thing, only you're not given a function or a graph, you're just given a table of values. And you're asked to approximate the area using a trapezoidal approximation with 6 subintervals. You can see from the chart or the table of values that it's a uniform partition, and the width of each trapezoid would be a half. So you would get 0.5 times the average of the first 2 y values plus 0.5 times the average of 4 and 6 plus 0.5 times the average of 6 and 7 plus 0.5 times the average of 7 and 4 plus 0.5 times the average of 4 and 1 plus 0.5 times the average of 1 and 5. And just for uniformity, I wrote that, the second last line there, I wrote that in a simplified form. So you can actually skip right to this line here if you ever wanted to. And when you do the math, you will get 12.75. It's really no different than if you're given a graph. It's It's the same process. You're just summing the areas of each trapezoid. Any questions on any of that? No? Okay, so just to briefly summarize, to approximate the area under the graph, we know 4 methods now. 3 of them involve rectangles. 1 of them involves a trapezoid. For the same number of subintervals, the trapezoid is a better approximation than LRAM and RRAM. And the relationship between the trapezoidal approximation is and the LRAM and RRAM is that the trapezoidal approximation is the average of LRAM and RRAM as long as it's the same number of subintervals. So those 4 methods you are responsible to know for the AP exam. Okay, part 2. So part 2 here focuses more on the applications of finding the areas under graphs and interpreting those areas. So what's the interpretation of the area under a graph? And I'll take you through a bunch of examples. Starting off pretty straightforward. So this is all in OneNote. So again, the whole point of this lesson or these printouts is when you find the area under a curve and it's in some context, what does that area represent? Okay, so it must represent something. And what it represents will depend on what the problem is about. So, first example, you have a graph, and it's just a speed graph, and it's just a straight line at 10 meters per second from 0 to 10, and I've highlighted the area under that graph. Okay, so it's just a straight line, a constant speed at 10 meters per second for 10 seconds. In a straight line. Determine the area under the graph over the interval from 0 to 10. So not difficult. It's just the area of this rectangle. So the area would be 10 meters per second multiplied by 10 seconds. That would be 100, and you can see from the unit analysis that the seconds disappear, they divide each other out, and our area represents, from the units you can tell that our area represents a distance, 100 meters. So what does this represent? It represents the total distance traveled over the 10-second interval. Which makes sense, right? If you travel at 10 meters per second for 10 seconds, you're going to travel a distance of 100 meters. So the area represents a distance traveled. One other important point I want to emphasize here, that this function, this speed function, speed is a rate. It's a rate of change. So we're going to be looking at examples where you're finding, keep in mind what we're doing here, we're finding the area under a rate of change graph. In other words, it's a derivative graph, right? We're used to calling a rate of change a derivative. So another way of looking at this problem is that I found, or we've found, the area under a derivative graph. The derivative of what? Or sorry, the area under the graph of speed, which is the rate of change of distance, since we're only moving in one direction. So when we find the area under a rate of change of distance, it gives us the change in the distance. In other words, I've traveled 100 meters. So just keep that in mind. We're finding the area under a rate function. So we'll go to the next problem. Slightly different, but the same idea, just packaged a little differently. The following graph represents the rate in liters per hour. So it's a rate of change function. That blue graph is a rate of change function. It's the rate at which methane is being produced in a cave over a 12-hour period. And that rate can be modeled by the equation there, 0.125 x squared plus 1. So one way of, I know it's just called f of x, but since it's a rate, you can imagine that that's the derivative of something. Okay? So part A says approximate the area under the graph using LRAM with 6 subintervals. So I've already drawn the rectangles. All we need to do is write an expression for that. So that area is going to be equal to the area of rectangle 1 plus 2 plus 3, 4, 5, and 6. But if I'm using LRAM, first of all, I guess we should find the width. The width is 12 minus 0 divided by 6. And you can see from the diagram that the width is 2. So it's going to be 2 multiplied by f at 0 plus f at 2 plus f at 4 plus f at 6 plus f at 8 plus f at 10. And now I don't have a answer for that. So I gotta figure this out on my calculator, I guess. So give me a minute. If you have your calculator there, you can try it and verify that I've done this right. I get 67. If somebody's actually verifying that, please let me know if that's not correct. I'm pretty sure it's right, although I might be wrong. So the answer, the area of that of those 6 rectangles is 67. But what are the units going to be? Well, for each rectangle, the height, what we're doing is we're taking liters per hour for each rectangle. that would be our height. And we're multiplying it by a time, which is in hours, which is our width, which would give us, because the heights would cancel out, that would leave us with units of L, which is liters. So the area of those 6 rectangles, what that represents is 67 liters. So what does that area represent in the context of the problem? It represents, liters is a volume, the volume of methane produced over the 12-hour period. So what we've done is we found the area under a graph or a rate, which represents how the volume is changing with time. So when we find the area under that rate graph, it's going to give us the change in the quantity which is changing, and in this case it would be volume. Okay, so you can look at that volume per unit time as a rate of change and think of it as a derivative. The derivative of what? It's the derivative of a volume function. It's how the volume is changing with respect to time. So the area under that derivative graph would give us the change in the volume. Any questions on that? So it's the same idea as the first example, just a different context. In the first example, we had a distance changing with time. And when we found the area under that graph, we got the change in distance. Now we have a volume changing with time, which again is a rate. And when we find the area under that rate graph, it'll give us the change in volume. And it's the same thing no matter what. That same pattern will hold true no matter what the rate is. Okay, next example. The following graph represents the rate, liters per minute, at which the volume of water in a tank is changing. So again, similar to the last example, we've got volume changing with time over a 6-minute period, and the rate can be modeled by that function there. Approximate the area under the graph using a trapezoid approximation with 6 subintervals. Okay, and then what does that area represent? So trapezoid is always the most labor intensive. So W is equal to 6 minus 0 and how many subintervals? 6. So W is equal to 1. So let's try and do this, skipping right down to the without summing areas. Let's try and write this in the condensed version. So this is going to be our width, which is 1.0 divided by 2. Okay, then that's going to be F at 0 plus 2 times F at 1 plus 2 times F at 2 plus 2 times F at 3 plus 2 times F at 4 plus 2 times F at 5, and then finally for the last one it'll just be F at 6. Okay, so what I've done is I'm writing this in, I'm taking a shortcut here. Notice all the inside partitions are multiplied by 2. It's just the first and last one that are singular. And then I just got to plug this into my calculator. So here we go again. I don't have an answer for this. So if you give me a minute, if anybody's there with a calculator, I would appreciate if you could verify this result. Okay, so there should be a negative out here in front of this. My apologies. There should be a negative sign out in front. Of the function. So it's actually negative 0.5 times x minus 2 squared times x minus 6. And when we do that, I got 18.5. I don't know if anybody out there has tried that. Anyway, that's not the important point. The important point is, what are the units here? So I'm finding, again, for each trapezoid, I'm taking heights, averages of heights. So I've added one height plus another height and divided by 2. But those heights are in liters per minute. And I'm multiplying them by a width, which is in minutes. And again, I'm going to get an area which represents a volume. So this is just 18.5 liters. So what does that represent? What it means is that 18.5 liters of, what is this, water? Have been added to the tank over the 6-minute interval. Okay, how do I know it's been added? Well, I got a positive number there. So again, I've got a rate graph which represents volume per unit time. And when I find the area under that rate graph, it will give me the change in volume. So the change in volume, the approximation for the change in volume is 18.5 liters. So 18.5 liters of water has been added to the tank. Any questions on that? Okay. The next, what do I got? 1, 2, 3 examples are for you to work on. Okay. So the first one, though, I just want to maybe give you some hints and how to start this. So you have a rectangular swimming pool, 30 feet wide by 50 feet long, and the table there is showing you how deep the pool is at 5-foot intervals, starting at 0 all the way to 50. Okay, keep in mind that the pool has a width of, or length, if you will, of 50 feet long. And so at every 5 feet, you're given the depth. So what I've drawn there, starting at 0, the depth is 6. So if you could imagine what I've drawn there, those lines, this represents the bottom, or an approximation for the bottom of the pool. At 0, the depth is 6. At 5 meters, the depth is 8.2. At 10 meters, the depth is 9.1. At 15 meters, the depth is 9.9. At 20 meters, the depth is 10.5. And you can do that all the way along to 50. So what you're going to do is, if you find, you're going to try and approximate the volume of water in the pool using LRAM, RRAM, and the trapezoid approximation. Now for the last one, keep in mind the formula that we discovered earlier, that the trapezoidal approximation is just the average of LRAM and RRAM. So what you're going to do is you're actually going to find the areas of these using whatever method. So there would be one, there would be the second one, third one. You're going to be adding up the areas of those rectangles, and then you're going to have to multiply by the width of the pool, which is 30, to get a volume. Okay, so that diagram there, adding up those rectangles from the picture won't give you a volume. It'll just give you a cross-sectional area. But the width of the pool is 30 all the way along the 50 meters. So you're just going to take that cross-sectional area and multiply it by 30. Right? What I'm saying is this. This is the 50. This is the 30. And we've got all these kind of things here. You're finding this cross-sectional area using the summing rectangles, and then you have to multiply by 30 to get a volume. So do that for LRAM, RRAM, and trapezoid. So do that problem and the last two problems, and we will take those up next class. We'll go through those. But please attempt the problems. Don't wait for me to do them. It's easy when I do them. It's another story when you guys do them, right? So you'll get more out of this if you actually try that. Try these 3 problems. So to summarize for homework, what have you got? You're doing these 2 integration problems. The answers are there so you can check to see what you're doing. And then try these 3 problems where you're approximating the areas or volumes in these 3 questions. And here's a summary. You can read the summary, that might help you. And that's it for today. Are there any questions on any of this? Or what it is that you need to work on? 2 integrals and 3 word problems, that's it. And I'll stop there. And we'll pick it up by taking up all of those next class. No questions? Have a great day, folks.
Thanks, Sarah. See you next class.
Thanks, sir. Have a good day.
Bye, sir.
Bye, sir. Have a good day.
Bye. Hmm. Uh-huh.
Big weekend, eh, sir?
Huh?
Big weekend, eh? With football.
Oh, yeah. Soccer, too.
Oh yeah, I saw Morris posted in
Yeah.
it's yesterday.
Yeah, the good part about that is that Atlanta winning against Milan.
Yeah.
Like, Milan lost, Inter tied, and Juventus won.
Yeah.
So
Oh, that's good.
that means they're out. They're moving. Juventus is catching up with them because Juventus is only in fourth place.
Yeah.
That's good.
And yeah, and then the football games. Kansas City's gonna win. I'm sorry.
I think
Yeah.
so too.
So too. But I did not expect Brady to pull that off. I thought the Packers were winning that for sure.
Yeah. I don't know.
Yeah.
It's a good game though. I like. I don't really care who wins. It's nice when it's close. The last
Yeah,
game.
yeah.
The last game got. It wasn't. You couldn't even watch the fourth quarter. Almost. It was. You knew it was over, right?
Yeah, that's true.
True. But there was some nice fighting there at the end. It made it enjoyable.
You love to see it.
I didn't see it. I didn't watch it.
Yeah.
There were fights.
They were good.
Yeah, like every minute there's another fight.
Oh, wonderful.
Well, the Bills knew that their season was over, so after every play they were just pushing and shoving. Like there was one play Josh Allen got sacked and then he just threw the football at the Chiefs guy's helmet and then like the
I didn't see that. Really, eh?
yeah,
it's like
and
a little
then
tap,
another
it just
Chiefs guy
stays-
and the best part like push him around for it and then a big Bills offensive lineman comes in like bull rushes the
Yeah.
Chiefs guy